In mathematics and physics, many quantities can usefully be represented as arrows, either 2D or 3D. So, for example, the separation between 2 points can be shown as an arrow of a particular length, say 5 meters, and pointing in a certain direction. And here we can see an arrow of length 5 meters drawn on a flat plane between the points A and B. In physics, we would call this a displacement vector. There are various ways to write a vector. For example, we can describe a displacement vector by its endpoints, or we could simply give it a name, such as bold A or A underscore. Now, since this displacement vector lies in a plane, we can show it relative to a set of xy axes. And now we can see that instead of going from A to B directly along the 5 meter vector, we can do it in 2 steps. First, we can move 4 meters along the x-axis, and then we can move 3 meters along the y-axis, starting at the origin and ending at B. And if we combine these 2 motions, we get the same result as moving from A to B directly along the diagonal. And having seen this, we can now write a numerical description of the vector. We write a column with 4 at the top, which means move 4 meters parallel to the x-axis, and 3 at the bottom, which means move 3 meters parallel to the y-axis. And we call this description a column vector. The numbers in the column vector show displacements and not coordinates, so the arrow shown here is represented by the same column vector. In fact, we could place the arrow anywhere in the xy plane and it's always represented by the same column vector. And similarly, all of these arrows can be represented by the same column vector, -2, 3. We see here the 4, 3 column vector that goes from A to B. In addition, we see the blue arrow that goes from A to P and the red arrow that goes from P to B. And we can note that those arrows are also displacement vectors. The blue arrow runs parallel to the x-axis, so its column vector is 4, 0. That's because it takes us 4 units in the x direction and 0 units in the y direction. The red arrow runs parallel to the y-axis, so its column vector is 0, 3. 0 in the x direction, 3 in the y direction. We see that travelling along the AP vector and then along the PB vector gives the same result as travelling along the AB vector, i.e. we combine the AP and the PB vectors to create the AB vector. This process of combining vectors is called vector addition. We can write this process as AP plus PB equals AB, or as 4, 0 plus 0, 3 equals 4, 3. 4, 0 is called the x component of AB, 0, 3 is called the y component of AB, and 4, 3 is called the resultant, which means the result of adding the x and y components. From a geometrical point of view, when we add 2 vectors, we place them head to tail, and we draw an arrow from the tail of the first to the head of the second. To add 2 column vectors, we add the x elements and the y elements separately. So 4 plus -2 is 2, 3 plus 3 is 6. And we could represent this geometrically as follows. And similarly, we could add the -2, 3 vector to the 4, 3 vector like so. And we could represent this addition as follows. This demonstrates that the order in which we add vectors is irrelevant. If we add a vector to itself, we create a vector twice as long and in the same direction. Algebraically, we would write v plus v equals 2v. So multiplying a vector by 2 stretches it by a factor of 2 in the same direction. And in general, if we multiply a vector by a real number a, we stretch it by a factor of a in the same direction, as long as a is a positive real number. Algebraically, to multiply a column vector, we multiply both components. A zero vector is an arrow of 0 length and with no direction, and to draw such a vector we draw a point, and we call it 0. The property of the zero vector is that if we add it to any vector, then we make the same vector. So 0 plus v equals v for any vector v, and we write the 0 column vector as 0, 0. If we add a vector and a vector of the same length but in the opposite direction, we create the 0 vector. And we call the vector that we added minus w. And by calling the added vector minus w, it allows us to write w plus minus w equals 0 in the same way that we write 3 plus minus 3 equals 0. We say that minus w is the negative of w. For column vectors, if w equals 4, 3, then minus w equals minus 4, minus 3. If we take a vector w and multiply it by minus 1, we can write minus w as the result in the usual way. And this just says that multiplying a vector by minus 1 rotates it by 180 degrees. And in general, if we multiply a vector by a negative number, it rotates it by 180 degrees and stretches it. So for example, if this is v, then minus 3v is this vector. When we multiply a column vector by a negative number, we multiply each of its elements by that number. We can subtract one vector from another, so to calculate a minus b, we actually compute a plus minus b. And we do that because we already know how to add vectors and we know how to find minus b. So for example, to find a minus b, given these two vectors, we find minus b, and then we take a, and we add minus b to that, head to tail, and compute the resultant, which is a minus b. Or alternatively, to find a minus b geometrically, we can place the vectors tail to tail and then draw the vector from the head of b to the head of a. To subtract one column vector from another, we subtract the x components and y components separately. If we wish to, we can split any 2D vector into components parallel to the x and the y axes, and this is called resolving a vector into its components. So here we see the 4, 3 vector, which we have resolved into a 4, 0 component and a 0, 3 component. The 4, 0 component is the x component, the 0, 3 component is the y component. And so we can write the 4, 3 vector as the sum of the 4, 0 vector and the 0, 3 vector. Similarly, we can split up the minus 2, 3 vector into a minus 2, 0 component, which is the x component, and a 0, 3 component, which is the y component. And thus we can write minus 2, 3 equals minus 2, 0 plus 0, 3. Now we can go further with this decomposition because each component can be written in terms of a unit vector, where a unit vector is a vector with length 1. And so we can write 4, 0 equals 4 times 1, 0, where 1, 0 is a unit vector. And we can write 0, 3 equals 3 times 0, 1, where 0, 1 is a unit vector. And along the same lines, minus 2, 0 can be written as minus 2 times 1, 0. The 1, 0 unit vector is usually called I, and the 0, 1 unit vector is usually called j. And so we can write 4, 3 in terms of unit vectors as follows. So 4, 3 becomes 4i plus 3j, and similarly minus 2, 3 can be written as minus 2i plus 3j. We can write minus 2i plus 3j graphically as so. The blue vector is I, the red vector is j, and minus 2, 3 can be decomposed into unit vectors as follows. Minus I plus j plus j plus j. So far, we've only looked at 2D vectors, i.e. vectors in the plane, but vectors can also represent 3D quantities. And any operation that can be applied to a 2D vector, such as addition, scaling, subtraction, and so on, can also be applied to 3D vectors. Whereas 2D vectors can be resolved into components parallel to the x and y axes, a 3D vector can be resolved into components parallel to the x, y, and z axes. And of course there is a unit vector in the z direction, which is called k. A 2D column vector has 2 rows, and a 3D column vector has 3 rows. So for example, we may have the vector 2, 3, 4, where 2 is the x component, 3 is the y component, and 4 is the z component. So to decompose a 3D vector, we use the I, j, and k unit vectors, and in column form, these are 1, 0, 0, 0, 1, 0, 0, 0, 1, which represent I, j, and k respectively. And graphically, we can represent the 2, 3, 4 vector like this, where the blue vector represents the x component, 2i, the red vector represents the y component, 3j, and the green vector represents the z component, 4k. And algebraically, we would write this vector either as v equals 2i plus 3j plus 4k, or as 2 times 1, 0, 0 plus 3 times 0, 1, 0 plus 4 times 0, 0, 1. Two vectors are equal when their corresponding components are equal, and this is obvious from a graphical point of view. Here we have the minus 2, 3 vector and the 4, 3 vector, and their y components are equal, but their x components differ, and so the vectors are different. In terms of column vectors, AB is equal to PQ if and only if A equals P and B equals Q. So if AB equals 3, 4, then A equals 3 and B equals 4. Or alternatively, if AI plus BJ equals 3I plus 4J, then A equals 3 and B equals 4. This process is called equating coefficients. Now we can turn this process around so that if we have a pair of numbers that are equal, such as p equals 5 and q equals 6, then the vectors that we construct from those pairs are also equal. So in this case, the vector pq equals the vector 5, 6. And the obvious 3D version of this fact is also true. So that if the vector ABC equals the vector PQR, then A equals P and B equals Q and C equals R, and vice versa. And so, for example, if the vector ABC equals the vector 3, 4, 5, then A equals 3, B equals 4, C equals 5. Or alternatively, if AI plus BJ plus CK equals 3I plus 4J plus 5K, then A equals 3, B equals 4, C equals 5.